So is it fine now? Cool. So hi everyone. Very good evening to you all. So myself Ayush Tripathi. Currently I'm working as a mentor and the problem setter at Geeks for Geeks. And I welcome you all to this post contest analysis session of last weekly contest 185. So before starting the discussion, I want you guys to rate the entire contest on a scale of 10 so that we can improve the problem set for the upcoming contest. And if you are rating less than or equals to 3, then please justify your reasons. And I personally categorized the entire contest from a medium to a hard level. The first three problems were totally based on observation. The last problem was bit hard, and it uses the advanced technique of DP with bit mask, which gonna be the prerequisite for the last problem. So if you do not know what is DP with bit mask, then you may skip the last problem, the fourth one. But for the first three problem, there is no prerequisite at all. You just only need to draw some observation and do some casework. So shall we start with the discussion? Or in case if you have any query, then please go ahead. I was able to solve only one question. Okay, that's great. First question was very tricky. No, you just only need to draw some observation. Now let me just share my screen. So this is the first problem. Array balancing cost. So let me go with this layout. Yeah, is it fine? So array balancing cost. So in this problem, basically you are given an array ARR of integers and length is n, and an array is considered balanced if elements at odd indices, and here one base indexing has been considered. So array is considered balanced if elements at the odd indices are odd integer and element at the even indices are even integer. And to achieve this, you are allowed to do the following operation any number of time. You can select any two indices I comma j, and then you can swap it their values. That is swap ARR of I and ARR of j. And the cost of this operation is simply equals to their sum, ARR of I plus ARR of j. And you need to determine the minimum cost possible to achieve a balanced array. That is, at odd indices we must have odd integers, and at even indices we must have a even integer. And if it is not possible, then just simply return return -1. So let's just look at this first example, 4 3 2 1. So array, we have a 4, 3, 2, and 1. So now here you can see this is position 1, index 1. Here one base indexing has been considered, then index 2, index 3, and index 4. And at index 1 we have even element, at index 3 we have even element, and at index 2 we have odd element, and at index 4 we have odd element. So basically all the indices are not satisfying the condition. We must have to change all the indices value. So what I can do, I can select one odd element and one even element, then I will swap them. So that is, you can just simply select these two elements and swap their values, and select these two elements and swap their values. So the resultant array would be 3 at index 1, which is an happy case. At odd index we have odd element, then at index 2 we have 4 even, and even index even integer. Then here at index 3 we will have 1, and at index 4, which is even, we have even integer. So this is a balanced array. And how much, what will be the cost in a cut? So in this case it is simply equals to sum of swapped integers. So 3 plus 4 and plus 2 plus 1, that is sum of this entire array, which is simply equals to 8. So now let me just check the expected output. So here it is, 10. So okay, it was my bad. So their sum is equals to 10. Cool. Now let's see how we can solve this problem. So let me just quickly draw some elements here. So let's say we have an array of 9 elements, and A1, A2, A3, A4, A5, A6, A7, and A8, and finally A9. So let's say at index 1 we have odd number, that at index 1 which is odd, and we have odd number. So let me just quickly write this as odd. So I'm writing this odd with a red pen, and I will write even with a green pen. And let's say at index 2 we have even number, so this is an happy case. And then we have odd, and let's say at index 4 also we have odd, and at index 5 we have odd, and let's say at index 6 we have even, and at index 7 also we have even, and at index 8 we have even, and let's say finally at index 9 we have some odd element. So what are the two indices which are not satisfying the condition? So here this index 3 and this index 7, these are the two indices which are not satisfying the condition. So my claim is that the claim is you have to select A1 and A3 and A7, then swap these two values, and this will give you the minimum cost. So why is it so? The idea is very simple. Just simply select one odd element and one even element and swap their values. Now some of you might wondering, is it possible to get the best answer via some different path? So it is not possible, because this will give you the minimum cost. If you select this A1 and some other element other than this 3, then also this value of A7 will be added in your cost. So that's why it's always best to select A3 and A7. If you select this A7, with some other element, because I know I must have to change this A3 and A7. So if you select this A7 with some other element, then also A7 will be added in your cost, because the cost of swapping is the sum of their values. So this will be added in every case. So that's why it is best to select A3 and A7. Now let's just consider the case when it is not possible to achieve the answer. So if the number of even elements, is not equals to n by 2, and basically it's floor value, and if you apply this operator, then it will eventually give you the floor value itself. So if it is not equals to n by 2, then in that case it is not possible to achieve a balanced array. So you can just simply say my answer is equals to -1. So let me give you some example. So let's say the value of n is 5. That is that is we have a1, a2, a3, a4, and a5. So how many even indices we have? So this is an even index, index 2, and index 4. This is an even index. So at least, not at least, but exactly I required two even values, two even integer. And if these two even integers are present anywhere in my array, then I will just swap some values and will bring it to their desired indices. Bring them to desired even indices. Yeah. So here in this case, you can see the value of the count of even, which is 2, and it is simply equals to n by 2. So it is possible to achieve the answer. And here n by 2 is simply 2. So this is the complete solution. Is it clear to everyone? Just write a quick +1 if the solution is clear to you, so that we can discuss the implementation. Let me just show you the implementation here. So yeah, this is the implementation for the first problem. So this minimum cost is the method that you need to complete. And here I have initialized my answer with 0. Then this is the size of the array. Then I iterate over all the indices from 1 to n. And here I have subtracted -1 because of zero-based indexing. So if the element value, that is if integer, is not equals to the parity of index, so this simply means the current index is violating the condition. So I will just simply add its value in my answer. And also I'm counting the number of even integers, and if the number of even integers is not equals to the floor value of n by 2, then it is not possible to have this answer. It is not possible to construct a balanced array. And now you can see, so here one more thing, that what will be my answer. So my answer is simply equals to the number of indices which are violating the condition, because no matter which two values you will select to perform the operation, you are always adding their value in your answer. So that's why it is simply equals to the sum of values where the condition is being violated. And its time complexity is linear, because we are just traversing over this array one time. So O of n, time complexity, and we are not using any extra space, so the constant extra space. Cool. Now let's just discuss the second problem, which is a weak subarray, and this is also a pretty interesting problem based on some observations. So here in this case, you are given an array of size n, and a continuous subarray is considered weak if the sum of its element is less than the maximum element in that array. And your task is to determine the minimum number of elements to remove from the array so that no weak subarray exists. Cool. So in this case, here if we can remove this 5, or how many minimum number of elements? we require to remove to such that no weak subarray exists. So here in this case, what we can do, we can remove this 5. If I remove this minus 5, then there do not exist any subarray which is weak. Cool. So let's just quickly draw some casework. So we need to remove the minimum number of elements. Let me just quickly write the problem statement. Remove minimum elements such that there do not exist any subarray in the resulting array which is weak. That is, we must not have this condition. A of 1, here I am considering the 1 base indexing. A of 2, A of 3, then some element A of I, and yeah, for all indices I, we must have their sum greater than the maximum element of this subarray 0 to I. So this equality must satisfy for all the cases. Then only I can say there do not exist any weak subarray. So now let's just draw some casework. So the very first case 1, what if the value of n is equals to 1? What if the value of n is equals to 1? So in this case, you don't have to remove any element, because if either it is a positive, let's say we have a 2. So here in this case, you don't have to remove any element, because we only have one index 1, and here the sum is greater than the maximum element, greater than or equals to the maximum element. Basically it is equals to the maximum element. Or even if it is negative, if it is, let's say, negative minus 5, then also the sum is equals to the maximum element, because we only have one element. So all the subarray of size 1 is always valid. It is not possible to have a weak subarray of size 1. So in this case, my answer is simply equals to 0. I do not have to delete any element. Now let's just consider the second case. And now I am assuming the value of n always greater than 1. Otherwise, it will be my first case. So now let's just consider all the values greater than or equals to 0 for all I in the range from 1 to n. Or I can write it this way: for all I in the range from 1 to n. Do not get confused. Here I have considered one base indexing. So what will be my answer in that case? So let me just draw some example. Let's say we have a 2, 3, 1, 4, and a 5. So in this case, what will be my answer? Now if you consider any subarray, then all the subarrays are not weak. All the subarrays are valid, because here all the magnitudes, here we all have a positive number. All the numbers are positive. So in this case, a of 1 plus a of 2, then some value a of I, this is always greater than the maximum element of this subarray. This is always true. This is always true, because the maximum element will be among these first I elements. And you have also added this a of I in your sum and some other elements. So the sum is always greater than or equals to the maximum element. A very basic observation. So in this case, I do not have to delete any element, so my answer is equals to 0. Now let's just consider the third case where all the elements are negative. So case 3, where all the elements are less than 0 for all I in the range from 1 to n. And here the value of n is always greater than 1. Also let me write this case. So n is greater than 1. So in this case, you have to delete n minus 1 elements. That is, your answer is equals to n minus 1. And let me just quickly write some example here. So let me just quickly write the same example. Minus 2, minus 3, then minus 1, minus 4, and minus 5. So here now you can see for all the index I, for all I, which is greater than 1, the sum of first I elements is always less than the maximum element. This thing, this thing is always less than the maximum element of this subarray. And this is basically a very simple reasoning. All the values are negative. So if you add some element, then your sum will be your sum will reduce. So if we have more than one element, that is, if we have more than one element, let's consider two elements. So in this case, your sum will be lesser than any values, any one separate value. So here in this case, let's consider this subarray. So here in this case, so the sum is minus 5, and what is its maximum value? Its maximum value is minus 2. So and this minus 2 is greater than the entire sum. So in this case, this is an weak subarray. This is an weak subarray. Cool. So here in this case, every subarray which is greater than 1 is weak. So that's why I have to reduce its size, the size of the array, to 1. And I have to delete n minus 1 elements from here. N minus 1 element. Delete these n minus 1 element, or you can delete any n minus 1 element. Because we have already seen this thing that subarray of size 1 is always valid. So this was the third case. Manas, you can watch the recording of the session once the class is over. So then case 4. Case 4, where when we have some odd elements and some even element. That is, when we have both negative and a positive element. So what will be my answer in that case? So let me just draw some array. So let's say we have a 2 positive number, then 5 positive number, then 3 positive number, and let's say minus 1, a negative number, then let's say 7, and let's say we have 5. So in this case, which subarray is valid? And what are the subarrays which are weak? How many subarrays here which are weak? So now here, if you can see, this subarray where all the elements are positive, it is an valid subarray, not a weak subarray. Then this is also an unhappy case, not a weak subarray, because we all have positive elements. So this is case 2. And here we all have positive elements. So this is also not a weak subarray. But now once I add some negative element, now my subarray is weak. And why is it so? So consider their magnitudes only. So A1 plus A2, or let me write with a red pen. So A1 plus A2 plus A3 and some value A of I. And here in this case, if you have any one negative element, then the subarray is always a weak subarray. So this sum is gonna be less than the maximum element of this array, this subarray. And how you can prove this thing? Just simply consider the magnitude of all the elements. So magnitude 2, magnitude 5, magnitude 3, then magnitude 1. And here the sign is minus. So this simply means I have to subtract this magnitude, right? So here this simply means I have to subtract this magnitude. And it simply means you are subtracting something. So you are reducing your sum. You are reducing your sum. And your maximum value will always be greater than that element. Because we have already seen this thing, that the value of n is greater than 1. That is, we must have two elements in an array. So if you select the minimum element, then your next element would always be other than minimum. So your this value will remain as it is, and your sum has reduced now. So in this case, what will be my answer? So here all the subarrays after this -1, after this negative elements are weak. That is, this subarray is also weak, and this subarray is also weak. So all such subarrays which has negative elements are a weak subarray. So here in this case, my answer is simply equals to count of negative elements. And this is the complete solution. Let me just again summarize all the 4 cases. So case 1, when the value of n is 1, so in that case your answer is equals to 0. You don't have to delete any element. Then case 2, if all the elements are positive, then also you don't have to delete any element. And case 3, if all the elements are negative, then we must have to delete all the elements. And because a subarray, if the subarray has more than if subarray has any element which is negative, and if its size is greater than 1, then it is always a weak subarray. So that's why I have to delete n-1 elements from the array, and we are left with one element, and a subarray of one element is not a weak subarray. Then the fourth case, when we have negative positive both, so in that case any subarray which consists of a negative element is always weak. So I have to delete all the negative elements. So this is the complete explanation. Let me just show you the solution here. So yeah, this is the method that you have to complete. So here I am having two variables, positive and negative. Both has been initialized with 0, and both will store the count of negative and positive number. So then taking the size of this array, which is, yeah, then I iterate over all the elements using a for each loop, and if the element value is greater than or equals to 0, then this simply means I got one positive number, so increment the variable value. Otherwise, I got a negative number, so increment it. And if we have a 0 positive number, then what does it mean? If we have all negative, so in that case my answer is equals to -1. So let me just quickly check the constraint. Yeah, my answer is equals to -1 and -1. So if the value of n is 1, then 1 minus 1, which is equals to 0. And if we have any positive number, then I must have to delete all the negative numbers. So that's why My answer is simply equals to the number of count of negative numbers, and the time complexity is linear. So is it clear to everyone? Okay, in this question they said that if the subarray sum is less than the maximum element in a subarray, yeah, if the subarray sum is less than the maximum element, okay, so someone has asked this question. So okay, actually it was my bad. Here I might messed up with their explanation, because here it is consider this case. So the solution is exactly correct for the case 4, where you have negative positive both. But here consider this case. Okay, consider the subarray of size 1, and it is 5. Consider the subarray 1 and 5. So consider this case 1 and 7. Here what is your sum? Here your sum is simply equals to 6 minus 1 plus 7. And what is your maximum element? So here the maximum element is equals to 7. So here this sum is less than the maximum element. So this is a weak subarray. Weak subarray. So that's why we must have to delete all the negative numbers. Is it clear to you, Hemant, now? Anyway, let's just discuss the next problem. Yeah, previously I have selected some different element, some different subarray which was valid. So yeah, it was my bad. So mana mastery, and okay, let me just read the problem statement. So in this problem, you are an adventurer traveling through a mystical corridor with the unsealed doors, and behind the ith door there lies a magical item that increase your power, mana, by its value, that is ARR of I. And to pass through each door, you must use one of two magical spells, and with its own trade-off. So every magical spell, one of two magical spell, has their own trade-off, their own cost. And the first magical spell, which is a purification spell, and this is a safe and reliable spell that open the ith door without affecting the other treasures. However, it requires k unit of mana per use. That is, if you use the purification spell, then your power will reduce by k, and you will get a of I. That is plus a of I minus k. And the second type of spell, the dark and powerful spell that open the doors for the free, that is you will get A of I, but weaken the magic of all the remaining doors, including the current door, and reducing the mana, yeah, reducing the mana of the magic item behind them to their half of their current values, that is A of I by 2, and weakening process round down to the nearest whole number, that is you have to consider the floor value of A of I by 2, and our goal is to maximize the power that we can achieve after opening all the doors. And this is very interesting thing, that you can draw upon extra mana reserves, that is in between the game you are also allowed to have a negative power at any ith door, and you must have to open all the doors in the same sequence as they provided. So let me just explain you this example: 3692 and the value of k as 4. So third problem, mana mastery. So here in this case, let me just first explain you what is the problem statement. So we have two types of operation, and we must have to perform any one of these two operation on every element of the array. So the operation of type 1, where you can just simply add A of I minus k in your answer, that is your power will increment by this value, and it might if it is negative, then also it is not a problem. You may have a negative power at some door I. Then type 2, where you can add A of I by 2 in your answer, and the rest of the remaining doors power will reduce by half, that is all the j's, that is we have to update, this is a update A of j as A of j divided by 2, this is j not I, that is half every value in the suffix from I to n. So for all j which is greater than or equals to I, this is simply means you have to change the suffix. Now let me just explain you the first example, where the array is 3, 6, 9 and 2. This was the array which is given to you, and the value of k as 4. So what I can do, I can perform the operation of type 1 on the first element, operation of type 1 on the second element, then again type 1, and then I will perform operation of type 2. So what will be my power at the end? So in this case my answer is simply equals to A of I minus k for the first type of operation. So 3 minus 4, and now you can see after the first door your power is negative -1. Then plus 6 minus 4 plus 9 minus 4, and then on the last element I have applied the operation of type 2. So this is 2 by 2, which is equals to 1. So in total this sum is simply equals to 1 plus 2 plus 5, this is -1 not 1, and plus 1, which is equals to 7. And this was the expected output, I guess. Yeah, 7 was the expected output. Purification spell on the first three elements, and on the last element, on the last door, apply shadow spell. Now let's see how we can solve this problem. So the observation here is that we always now please try to pay more attention. The observation here is that we always divide the subarray, divide this entire array, not a subarray. We always divide this entire array into two parts, and on the first part, I will apply purification spell, that is operation of type 1, and on the second part, I will apply the second type of operation, that is a shadow spell. And I will also give you the proof that if you apply a shadow spell, that is if you have used the operation of type 2, then it is not optimal to use operation of type 1 after using the operation of type 2. So what I'm trying to say, consider every partition of this array. This is my array A, and divide this array into two halves. So let's say this is a current index I. So from I to index n, and from 1 to index I minus 1. Here I will apply operation of type 1. Operation of type 1, that is a purification spell simply. And on the remaining part, that is on the remaining elements from index I to n, I will apply operation of type 2. Type 2, that is a shadow spell. Because here the value that you are subtracting when you apply operation of type 1 is k, and this is constant throughout this entire array. The value of k is constant. So it's always beneficial to use the operation of type 1 as early as possible. And if at any point of time you have decided to use a operation of type 2, then do not use operation of type 1 anymore. So let's consider a very basic example. Let's say we have only two elements, A1 and A2. Now, for these two elements, what are the possibilities we have? So the very first possibility, when I use the operation of type 1 on the first element and operation of type 2 on the second element. That is first purification, then shadow. Then second possibility, when I use operation of type 2 on the first element and operation of type 1 on the second element. So which one is better? My claim is, my claim is always using purification spell at the beginning is always beneficial. And yeah, so here what will be your answer? So you have used the purification spell on the first index 1. So this is A1 minus k, and on the second door, or basically the second element, I have used the operation of type 2. So how much cost I will get? So this is simply A2 divided by 2. Cool. And here in this case, my answer is simply equals to A1 divided by 2, then plus A2 divided by 2. Because if you have used the operation of type 2, then you must have to divide all the elements in its suffix, and minus k. And it is clearly visible from here that I can write in this way: A2, then plus A1 divided by 2, then again A1 divided by 2. I have just basically simplified this and divide this A1 into two half, minus k plus A2 divided by 2. and here it is. Let me write as it is, and minus k. So here we can, it is clearly visible that this a1 by 2, this a1 by 2 will get cancelled out, then minus k will get cancelled out, a2 divided by 2, a2 divided by 2 will get cancelled out. So now we are left with a 0 and a1 divided by 2. So that's why it is this using purification spell at the beginning is always optimal, to use after the shadow spell. And it is very obvious that if I have used the shadow spell first and then I use the purification spell, then it does not make any sense, because this constant k, this k is constant. So just try to subtract this k as early as possible, so that we get rid of this division part. So I hope it is clear to everyone. Now, yeah, this is the complete solution. Now for every index I, on the first I minus 1 elements, that is from 1 to I minus 1, I will apply operation of type 1, that is purification spell. Then from I to n, I will apply shadow spell. Cool. Now, now this is the next and final observation. The value of a of I, let me just quickly check the constraint. Yeah, the value of element can be up to 10 power 9. So a of I can only be up to only be up to 10 power 9. So less than or equals to 10 power 9. Then and we know that 2 power 30 is greater than 10 power 9. So if you divide 10 power 9 by 2 power 30, then the result is always 0. The result is always 0. So in this case, my claim is that after the 30 elements from index I, all the values are 0. So that is, here you will divide by 2, then here also you have to divide it by 2, because if I am not performing the operation of type 1, then I must have to perform the operation of type 2, that is again divided by 2. So this is 4, then this is 8, then this is 16, and so on up to 2 power 30. And after this, all the elements will turn to 0, will turn out to be 0. So just only consider the 30 values from this I. So from I to I plus 30. This is enough. After this, all the values will be 0. So let me just show you the implementation. Yeah, this is the implementation. Make sure to use the appropriate data type, because your answer may be very large. So this is my answer. And here I am building this purification spell that I have used on the previous elements in a progressive order. So I have initialized this one with 0. And from index I to n minus 1, I will use the shadow spell. So this is my shadow spell value that I will get if I use the shadow spell from I to n minus 1. So here I know I will iterate from j is equals to I, and it will go from I to I plus 31 at max, and minimum of I plus 31 comma n, whichever is minimum, because after 31 I plus 31 it does not make any sense, because all the values are 0. And then I am just adding the floor value of a of I divided by 2 power j minus I and plus 1. Cool. And taking its floor value. So here I have used the left shift operation. but you can also divide it by writing some other function or using arithmetic operator. So this is the in occurred profit from element ARR of j, and then I will just simply add this value in my shadow variable. And finally, I'm taking the maximum at every index I. At every part, I'm checking for every possible partition. Otherwise, before moving to the next element, now I have decided to use this index, use a purification spell for this ith door. So in that case, ARR of I minus k, I will add in my answer in my purification variable. And this is an edge case that you might have missed. So there might be the possible when you will open all the door using a purification spell. So that's why all the doors from 0 to n minus 1, and the maximum answer that I have so far, comma this edge case, and finally I'm returning this answer. And what will be the time complexity? This is very straightforward. It is n multiplied by 31. N multiplied by 30. Yeah. So is it clear to everyone? Just write a quick +1 if this solution is clear to you. I didn't understand. So you can watch the recording of the session. Just write a quick +1 so that we can discuss the last problem of the contest, for which the prerequisite is DP with bit mask. So this is the final problem of the contest, and this is the most hardest problem of the contest. So expecting a very high level attention from you guys. So please try to pay more attention. And I am assuming that you all guys know about this DP with bit mask. So card flip. So you are given n cards arranged in a row, and each card has a number on the front and the number on the back, represented by two integers array of the size n, both, and front of I will simply represent the number which is written on the front of ith card. So for ith card, front of I is the number on the front and back of I is the number on the back. And initially all the cards are placed in placed with their front side visible, and you can perform the following operation on the card. You can choose any card at position I and swap this card with the I plus 1th card, and after swapping, flip both the cards so that opposite side will become visible. So if you select some index I, then you have to swap the value of I and I plus 1, and then also flip their visibility. That is, if it was front, then change it to back, and if it was back, then change it to front. Both the cards, I and I plus 1. And you need to determine the minimum number of operations required to arrange the cards such that the numbers on the visible sides are in increasing order, in a non-decreasing order, that is simply increasing order. And if if arrangement is not possible, then simply return -1. So let me just explain you this test case 413216. So 4 1 3, then 2 1 and 6. So in this case, we need to report the minimum number of operation required to sort the cards in a non-decreasing order, that is increasing order. And initially, the front side of the card is visible, that is 4, 1, 3 is visible to you. So what I can do, I can select these two cards and swap them. So it will be converted to 1, 4. And then what I will do, I will, okay, I have swapped these two cards and these one. So now I have swapped these two cards, and then I have to also flip the value. So I have changed the position of the first card and position of the second card. So the back value of the second card is 1. So this will simply change to 1, and then back of back of the second back of the first card, which is now at position 2, will simply it is 2. So this is simply 1, 2, and 3, which is a sorted array. All the elements are increasing order, and my answer is simply equals to 1. I have applied only one operation. So 1 is the expected output. Now the next thing is to analyze the constraint, which gives you an idea how to solve this problem. So n is only up to 16, and whenever you get this the value of n around 10 or 15, then you may think of a recursion backtracking problem solution. And the value of a card at front and back both can be up to 30 only. So let me just write the constraint. The value of n can be up to 16, and the value of front of I and back of I both can be up to 30. That is, yeah, up to 30, all the integers. So now what I can do, I can try out all the possibilities, and to try out all the possibility, you can write some recursive solution of exponential time complexity. Not exponential, basically I have to test every permutation, right? So if I have to test every permutation, then this is a factorial time complexity. And we all know how we can convert the factorial time complexity solution to an exponential using DP with bit mask. This is the key idea of a DP with bit mask. I have to try out all the possibilities, and what are all the possibilities? That is, I have to test all the permutation of the array, because there might be the case when you have to bring this last card to the front, and the second card to the last, and this first card to the second position. So this is might possible. So that's why I need to check all the possible permutation, and the permutation solution can be converted to the exponential using DP with bit mask. So now let's just define the state. So the very first thing, and basically in most of the DP with bit mask problem, you need to track the last value that you have changed. So let's just define a DP as val and mask. So DP of val comma mask will just it will simply store. So now I can remove this constraint. So it simply store minimum number of operation required to short the picked card in in increasing order, or you can say a non-decreasing order. Increasing or strictly increasing, both are non-decreasing. Increasing order such that value of either front or back, value of last pick card is val, is this val, And how you will get this thing, how you will get this a picked card value? So you will get this thing via this mask. Mask simply means hiding some information inside it. So let me just give you some examples. So let's say dp of 3 comma 22, and let's say it is equals to 5. So in this case, what does it mean? It simply means minimum 5 number of operation we required to short the picked card. And what are the card here I have picked? So it will be given by this mask. So what is the binary representation of this 22? So this is, I guess, 16 plus 4, which is a 20, and plus 2. So this is 1 0 16 plus 4 20 and plus 2. So this is the binary representation, and bit 0, bit 1, bit 2, bit 3, bit 4. So now please try to pay more attention. Bit 0 simply means card with the index 0. Bit 1 simply means card with the index 1. Bit 2 simply means card with the index 2. Cool. And what are the card here I have picked? So here I have picked the card with the indices 1, 2, and 4. And to short these three cards, and yeah, to short these three cards, the minimum number of operation that we required is 5. And the last value that I have picked is 3. The value of last card that I have picked is 3. So now you can see it can be any permutation. It can be any permutation of 1 to 4. So let me just draw in this way. So card 0, card 1, card 2, card 3, card 4, and let's say card 5. Cool. So here so far I have picked 1, 2, and 4. These three cards I have picked. And to short these three cards, you will require minimum 5 operation, and it could be any permutation of these three number. That is, it could be either 2, 1, and 4, or it could be 4, 2, and 1. So basically any permutation of these indices, because there might be the case when you have to move this card at this position, and this card at this position, and this card at this position. So that's why here it could be any permutation. And yeah, I hope it is clear to everyone. Now, before discussing the transition, let me just discuss the base case. What will be my base case? It is simply dp of 0 comma 0. dp of 0, what does it mean? This is the value of mask, right? This is the value of mask. And if the value of mask is equals to 0, this, this simply means I didn't pick any card. So if I didn't pick any card and the last value was 0, so how many operation I required to short the 0 card? It is already shorted, right? If you do not pick any cards, so I can say it is already shorted. So that's why dp of 0 comma 0 is simply equals to 0. Now let's just build the solution. And we all know how many possibilities we have for this mask. So the number of possibilities for this mask is from 1 to 2 power n minus 1. And these are the basically a very basic thing of dp with mid mask. So I'm not going to explain you this. Why it is 2 power n minus 1? Because I have to cover all the possible subsequence, or you can say all the possible subset, not subsequence, all the possible subset, all the possible collection of the cards. Cool. So let's just consider the mask value as 0. The mask value as 0. So what does it mean? It means so far you didn't pick any card. Now what if I pick the card with the index 0? What if I pick the card with the index 0? So if you pick the card with the index 0, then this simply means then it is already shorted, right? If I only have one card, then it is already shorted. So my value will remain as it is. I do not have to flip this. Now, what if I pick the card with the index 1? So this simply means I have to move this card at the front. I have to move this card at the front, and I have to perform one swap. Please try to pay more attention. Do not get confused with this thing. This is very, very important to understand the entire solution. What are the bits are set? These cards I have moved at the front. These card I have moved at the front, and so that I can say they are shorted. So that is, here I have moved this 1, 2, and 4. And this could be any permutation, 2, 4, and 1. But I am assuming all the three cards, all the bits which are set are at the front. All these three cards are at the front of the decks, you can say. Anyways, so yeah. So here if I select this one, then what does it mean? If I select this one, this simply means I have to short this, and it is only one card, so I can say it is already shorted, but I must have to move this at the front, and move this at the front, because previously I had a empty array which was already shorted, and I have to move this, shift this element. And since I have to perform one swap operation, so you will just simply swap these two values, so it will become 1 and 0. And you also have to select its value as back of 1, because if you swap this card, then you must have to flip its value. So the value that currently we are having is back of 1, not front of 1. Cool. And let me give you some another example. Let's say we are at index 2. We are at index 2. So if I have to short this, then, and all the previous cards we haven't picked, so I must have to move this card at the front. So for this thing I need to perform two swap. That is, swap these two cards, and then swap these two cards. So what value we will get? So if I swap this card two times, then its value will flip to two times, right? So in that case, you will again get the front of 2, because you have flipped this card two times. Cool. So yeah, these are some basic observation. Now let me just write the exact transition we could have. So let's say DP of 3 comma 22, the same example. And the binary representation of 22 we all know, that is 10110. So let me just draw a 6 card. So this is a card. All right, so yeah, this is a card with the index 0, then a card with the index 1, then card with the index 2, then card with the index 3, then 4, 5, and let's say 7. So index 0, index 1, index 2, index 3, 4, 5, and 6. That is 7 card, 0 to n minus 1. So this is index basically bit 0, then 1, 2, 3, and 4. So what are the cards I have picked so far? So far I have picked a card with the index 1, then card with the index 2, and the card with the index 4. Cool. So that means I know these picked card are being already shorted, because this value is stored in DP of 3 comma 22. I know these cards are already shorted, and these are at the front. So that is, we have 1, then maybe 4, any permutation of these three cards, and then 2. Now the new card that I will add at here, I will add my new card at here. My new card at here. Here I will add my new card. Cool. So far how many cards I have picked? This is simply equals to the number of set bits in mask. So let's call this as let's call this as pose. as per my implementation. This is simply equals to number of set bits. Set bits in my mask. Cool. And for this particular example, this is 3. Now, what I can do, I can just iterate over all the indices. I can iterate over all the indices for k is equals to 0 and to n minus 1. Why I have named this as k? Because as per my implementation, 0 to n minus 1. Now what here I can see, that this card 0, let me just yeah, okay, let it be as it is. So here what I can see, I haven't picked the card 0. But what if the bit 0 was already also set? So if the bit is set, then it means you have picked the card, and it is sorted. So just simply skip this bit. If I am at bit 1, then this simply means I have already picked the card. So just simply skip this bit. But this is bit 0. So this simply means I haven't picked this card 0, and I have to move this card 0 here, right? At the end of previously picked card. At the end of previously picked card. So how many operations do we require? How many operations do we require? So let's call this pose, which is equals to 3, and plus what? So this card has been moved to here. This card has been moved to here, and this card has been moved to here. So this simply means my card 0. Okay, so yeah, these 3 cards. So the number of, okay, how many swaps do you require? It is simply equals to the number of unset bit in between. Let's say I have to move this card at this position. All right, so there was a connectivity issue from my end. Really sorry for that. So hopefully it is fixed now. Okay, so where we are? Yeah, here. So far I have selected the card. Okay, let me just quickly check if I am audible. All right, so everything is perfectly fine. So yeah, now let's just get back to the solution. So far I have picked the card with the indices. Okay, I forgot to share my screen. Yeah, it is visible. So far I have picked the card with the indices 1, 2, and 4. Cool. And it could be any permutation of these three cards. Now, once I get this new card, the card whose bit is not set, that is this card 0. So for this card 0, is bit is not set. And how I can check this thing? So this is simply equals to mask and one left shift K. Or you can just simply apply a right shift on this mask. So let me just apply a right shift here. So mask, then right shift, a K time, and then take a AND with 1. And if the result is 1, then it means the bit is set. And if it was 0, then this simply means the bit is not set. So for this case, the mask, the value of K is 0, right? So that is, I will just simply take a AND with 1. Because if you apply a right shift operation 0 time, then the result would remain as it is. So here, if you take a AND, then it will just simply give you what is the bit at this position 0. If it was 1 in mask, then it is 1, and if it was 0, then it is 0. And here in this case, it is 0. So this is 0. So this is unset, right? So this simply means I have not picked this card. But what if I pick this card? So if I pick this card, I must have to add this here. I must have to add this card at the end. Now, what will be its value? What will be its value? So the very first thing, I know how many operations do I require, because after this I know my all the three cards are at the front. That is this card here, this card here, this card is also at here, and this card is at here. Cool. And then I have this as 0. So my post, the value of post is simply equals to the number of set bit, and then I will add the value of K. So that is 0, 0 plus post, and which is equals to 3, and 3 is an odd number. So if it is an odd number, then this simply means you have flipped the card for odd number of times. You have flipped this card because first you have moved this 1 here, that is on the left hand side of 0, then you have moved this 2, then you have moved this 4. So this simply means 0 plus 3, and take a mod with 2, and if it is equals to 1, then this simply means All right. So yeah. So this is simply equals to 0 plus 3 and then take a mod with 2. And if this mod value is 1, if this mod value is 1, then this simply means that the card has flipped. If it is 1, then this simply means card has flipped. And if it was 0, then this simply means the card has not flipped. We have flipped the card even number of time, so it will again back to the front. So in this case, you have to select the back value, and in this case that is back of I, and in this case you have to select the front value, so front of I. Cool. Now let me just move to the next index, and basically how I will update my DP. So I will just simply update DP of DP of which state I will update. DP of current mask, right? And since I have picked one unpicked card, so this simply means I have to make this bit set. I have to set this bit. Cool. So that is I have to make this bit set, that is a plus, or you can just simply say or one left shift k. Make this bit set so that this will be this mask which is 22 will get simply converted to 1 0 1 1 and 1. That is, you have selected card 0 1 2 and card 4. Very straightforward. And before that we have this val. So let's call this as let's call this value, that is the value of card after flipped or not flipped, as well. That is this value as well, either this one flipped or not flipped, based on the value of a post plus k. Based on the value of post plus k, this is simply post plus k, parity of post plus k. So this is k plus post. Based on the value of this thing, I will select either front or back. So let's call this as a val. So in this case, the last card that I have picked is having value val. And for this thing, what will be my transition? So now you can see the last card that I have picked is val. But before that, when I had selected the three cards, when I had selected these three cards, that is 4, 2 and 1. So in that case, what could be the last value that I can use? So this is simply equals to all the minimum values. Cool. That is whichever will give me the minimum. So let's call this as DP of X comma mask. And here I will select a minimum, because for the last three cards we could have any value which is less than this val. So minimum of DP of X comma mask, and for all the values of X which are less than or equals to this val, less than or equals to val. Because if previously you have a 2 3 4, so if these are the values of last previous three cards, that is 4, and the new card that you have added, you can add this new card with the value 4 5. You can add this a new card with the value 4 5 6 to maintain the increasing order. That's why X can be anything from 0 or from 0 to val. Cool. And how much operation do I require to move this kth card? So this is simply equals to the number of unset bit, the number of unset bit. And since here I have the unset bit before k, so since here I do not have any unset bit previously, so that's why it is 0. And how I can compute this thing, the number of unset bit before k, so plus number of unset bits before k, because there might be the case. Okay, let me just explain you with some different example. So here, let's say the value of k, these are the values that I have picked. The value of k is 5. The value of k is 5. So k is equals to 5. Cool, that is we are at here. And I know I have picked 1, 4 and 2. So now I have to move this k here. This card after this these three cards, these three picked card. So how many swaps do I require? So it is simply equals to the number of unset bit before k. And how many bits are unset before k? So I have these two bits unset. Cool, because you will move this. Now I know I have moved these three cards, 1, 2 and 4. I have moved these three cards, 1, 2 and 4 at the front. So that is, this card is at the front, this card 1 is at the front, this card 2 is at the front, and this card 4 is at the front. Cool. So now I have this card, this, let's say 1, 2 and 4. Now you have a 0 and 3. So now I have to move this 5 at here. So for this, how many swaps do I require? It is simply equals to the number of unset bit. So, and how I get the number of unset bit? So you can simply use the formula, which is a complement of mask, that is set all the bits, and then and with one left shift k, not k, I guess, yeah, one left shift k minus 1. Take a complement, take a and with these two value. So this simply means to set all the unset bit, and here simply means to set all the bits before k. So this is simply 2 power k minus 1, set all the bits before k. So all the bits set, and then you are taking the and with the set bit which are unset in the original mask. So you will eventually get the count of unset bit. These many swaps you required. So this is a complete solution, and talking about this problem, you can just simply use the absolute value, because there might be the case when you have to move the element k on the right side, or you have to move the element k on the left side. So you can just simply select the ABS of pose minus k, and then take a mod with 2. And why here I have used minus k? You can either use a minus k or the plus k. Both will give you the same parity. Cool. So yeah, now this is the complete explanation, and it was a bit hard problem. So you can watch the recording of this session after this session. So yeah, this is the function. This is the method that you have to complete. So first I have taken the size of the array. Then this is my infinite. This is my infinity. For initially, I will set all the DP values with the infinity. Then here is my DP array of size at 30, of size 31 multiplied by 2 power n. Then this is my base case. Then I iterate over all the mask from 0 to 2 power n minus 1. Cool. Then first here I'm finding the value of post, that is number of set bit. Then I iterate over all the indices, and if the bit is set, then skip it. And if it is not set, then it means I'm going to move this kth card at its correct position. Cool. Then this is my value of val, that is what will be the value, my value. So it simply equals to, if the parity is 0, then I will just simply select front of k, that is the card has been flipped even number of times, so it will equals to the initial value. And if it is odd, then it simply means it is equals to the, it is flipped odd number of times, so back value I have to select. Then here I have used the minimum value as infinity. Then I'm finding the minimum value of dp of l comma mask, and the value of l is in the range from 0 to, well, I have selected because as I have explained, that is for the previous card the last value could be anything, right, in the range, because the new card that I'm going to add is having value val. So the last card could have value anything less than or equals to this val, so that we could have this increasing order. Cool. And then I'm just simply finding the number of what will be my How I will update this thing? Basically, this is the problem. This is the, yeah. How I will update this thing? So the last value that I have picked is val, and I am setting this kth bit in the mask, and it is equals to the minimum answer that we have so far, because we could have any minimum answer that we have, because we could have any permutation. So that's why there is an overlapping sub problem, and you can memorize it further. And plus minimum value, basically this value, and plus the number of unset bit. So here I'm taking and with and of mask, complement of mask, and 2 power k minus 1, and the number of set bits here in this case. So this will be my, these are my transition, and what will be my answer? I have to pick all the n cards, so that is 2 power n minus 1 will be the value of mask, and the last value could be anything, so 0 to 30. So that's why here dp of val, where val can be from anything 0 to 30, and I have to pick all the n cards. And if the minimum result is still greater than or equals to infinity, then my result is -1. That is, I didn't get any answer, otherwise I will return this minimum result. Cool. So what I would suggest, just simply take your time, and think about this approach, how I am solving this problem. But in case if you are not aware about this dp of with mask technique, then you may skip the solution. It's totally fine. And the time complexity, it is simply equals to the number of different states that we have, which is 30 into 2 power n, and n can be up to 16. So it is a feasible time complexity, and it will pass all the test cases. So yeah, this is the complete explanation from my end. And in case if you are having any question, then please go ahead. Otherwise, we can wrap the session. Feel free to ask your question. Cool. So yeah, this was all from my end, and I hope you guys have enjoyed this session. And thank you so much, guys, for joining this session. And have a good day.